All right, welcome back. So here is our base structure for our max binary heap class. It's very simple. We are implementing only a max binary heap, but to change it over to a min binary heap or to make a min heap is very simple once you know how to do max. So either one could have worked. So we define the class, max binary heap, and the only property it needs in the constructor is a values property. So values will start as an empty list or an empty array, and that's it. We don't need to make a node class like we did for our other tree. We don't need to make a node class like we did for linked lists. We don't need previous pointers or next or left or right. All that we need is an empty array to start. And in this video, I'm going to walk through how we would add an insert method so that we could say max binary heap.insert 10, max binary heap insert 50. And we'll just be storing things in this values array, just like I showed you here, where we can take, instead of having to create a bunch of nodes and connect them manually, we store them in an array and we use their position to model the actual structure. The position, their index, the individual numbers corresponding to each item's position is what actually gives it the structure of the heap. So we'll move things around and swap them. So to make something else's parent, it just goes to the correct index. So we'll come back to that. But that's all that we need to store is an array of values. Okay, so as far as the process to insert something into a max binary heap, it's a little bit more complicated than a binary search tree, but it's still, I think it's relatively, I won't say straightforward, but it makes sense if you think about it. It's logical. So what we do, we fill it out from left to right. So all that honestly means, if we have an array like we have here, if we're trying to insert something to the tree, the only place for it to go is at the end. So we just push on to our list. We just do a array or list.push the new value, whatever it is. Now, of course, it's most likely not going to be in the right spot right off the bat. Let's say we push in 500. Well, that is the largest value in here. 500 is going to need to work all the way up to the top. So we add it to the end, and then we do something called bubbling up. And what that means is basically we swap it until it finds its final correct resting place. In a max binary heap, the larger values are going to bubble up to their correct spot. So what that looks like, if we were to step through it, if we add 55 to the end of the list to our array, this is what we're actually storing in our class. This is just a nice visualization, but this is what's stored. 55 goes to the end. That's not the right spot, but we just put it there to start. And that means by putting it here, its index means it is a child of 33. So this is index of 2 right here. So its children are at index 5 and 6. 2 times 2 plus 1, 2 times 2 plus 2, right? So this is 0, 1, 2, 3, 4, 5, and 6. Those are the two children. As we can see here, it's all set up correctly. Okay, so next we bubble up. And what that means is we take this node and we compare it to its parent. So we compare 55 to 33, and we swap them because 55 is larger. There's a little swap. It's not quite an animation, but you can see it there. And the change is reflected here. So before we had 55 as the child of 33. That was not the correct place. We just put it in without caring. Then we compared it to the parent, and we swap. Then we compare it to the parent again. How about 41 and 55? Well, we swap them. So now our data structure looks like this, where we have 55 as the root, and its two children are 39 and 41. All is good. Everyone's happy in the world of our max binary heap, because now every node satisfies the property that its two children must be less than the node itself. So again, we insert, and then we bubble up by swapping. And this is why it's important when I talked about how you could find a parent based off of a child. So if we had, like we had here, 55, we add it to the end, we need to find its parent at 33 and compare them. Then we swapped them. Then we need to find 55's new parent, 41, and compare them. And we swap them. So here's an animated version on Visual Algo, Visual, whatever it is. They give you numbers here so you can see the actual order in the array, in the list that's underlying it. So if you would read it, left to right. This is the first item, then second, third, and so on. So if we were to insert a value, let's say 26 is not going to be exciting. Let's do, how about 100? To insert that, the very first thing we do is add it to the left. And the way we add it, it always goes to fill out the left first and then the right. And that's, I mean, we're using an array. So just by adding it to the end of the array, by pushing onto it, it's going to be added here automatically. Okay, so we start here, and then we're going to compare it to its parent, 144. This is a max binary heap, so we are going to swap them. And now we take 100 and compare it to its new parent, which is 70. Well, 100 is still larger, so we're going to swap them. And now we take 100 and we compare it to 99. It's larger, so we swap them again. And now we're done. And this is our new max binary heap. If we insert another value here, like 15, it's going to go right there, and that's where it stays, at least for now. If we were to insert another one, it goes to the left, and it stays there. Let's do a larger value. Sure, 58. We insert to the right, we swap, now we're done. So again, there is no order between the left and right siblings. There's no shared property other than that they are less than their shared parent in a max binary heap. Okay, so the pseudocode to do this, here's the simple version. You just write a method called insert. It accepts a value. We're not working with nodes or anything. It just accepts a number. Insert 10. You add 10 to the end of the values array. You just push 10 into values. And then you bubble it up to its correct spot. So that's the more complicated part. It's easy to add it to the end of the tree, super easy, or the end of the heap. To get it to go to the right spot, it's a little more work. So here's some more detailed pseudocode. If you would like to do this all in one method called insert, you can do that. You could also write a method called insert, which calls another method called bubble up. Totally up to you. But the way bubble up will work, once you push the value in to the end of the values list or the array, it's at the very end, and it's probably in the wrong spot. It could be in the right spot, but it's most likely in the wrong place. So here are the basic steps. You're going to take the item at the last index, the end of the array, the very last thing you added in, and then you're going to find its parent. Remember the math that I showed you. Index minus 1 divided by 2, and you floor that. So that gives you the index of the parent. And then you just compare the value at that index compared to the value that you just added to the end of the array. And then you see which one is larger. It's a max binary heap. If the one at the end we inserted is larger, we swap the values. If it's not, then stop, you're done. It's in the right spot. And you keep repeating that process as long as the values element at the parent index is less than the values element at the child index. Or the other way around, as long as the child is larger than the parent, keep swapping. So you'll swap, and then you'll reset the index to now be the parent index. So you're moving it, right? So if we went back to this example, the very beginning, we add 55 to the end, we find its parent. Let's just look down here. So we add 55 to the end, we find its parent based off of the index, we subtract 1, we divide by 2, the index is this item at the value is 33, index is 2. We compare, 55 is larger, so we swap. Now the index that we're looking at is this index here, 2. And so now we find, using that number 2, we find the parent. So 2 minus 1 gives us 1, divided by 2 gives us 0.5, floored gives us 0. So the index now that we're comparing it to is index 0. And we compare these two items, and we end up swapping them. And then we stop because there is no next index to look at. There's no parent of this. So you could add that into your code, make sure that it accounts for that and it doesn't break, or you don't hit it undefined or something. Okay, so those are the basic steps. Again, insert, just push to the very end of the list or the array that you're using to store the values, and then bubble up. And here's a pseudocode for bubble up. So try it on your own. Write 2 methods if you prefer, or do it all in one insert method. In the next video, I'll have an implementation.